All right. So the panel today is going to focus on some of the key impacts areas of green roofs and green walls, which I refer to as vegetative envelope components. And we want to talk about sort of what the types of impacts are, how you can predict the impacts and the performance, what kinds of factors affect them, and how performance can vary in different locations and so on. And as kind of a conclusion in the discussion today, we want to go into sort of how some of those things can be taken into account from a more holistic look at buildings as systems. We have an illustrious panel today. I'm really impressed with all the people who are on this panel. I want to introduce them. First, Bob Cameron, who for more than 2 decades was Director of Environmental Programs for a large multinational firm. He's had all kinds of experience on doing a wide range of things from bioremediation to designing green roofs and living walls, constructed wetlands, and so on. Our second speaker is Dr. Karen Liu. She's with Bonar Zero Floor, and she's been doing research on green roofs since the early 2000s. And I remember using some of her research several years ago when I was working on some projects. And our last speaker is Chris Wark, who's done a lot of engineering work over the years, very experienced also in a wide range of things related to green roofs and green systems. And I remember using his Shade computer program several years ago as well. So I think we've got a very qualified group of people today to talk about the topics that we want to address. And to provide a little bit of background, this topic kind of came together by considering some of the issues related to vegetative envelope components and some of the areas that I've been working in since, say, early 2000s as well, looking at the economics, the different types of impacts of green roofs in terms of energy and in terms of wastewater treatment. And how you actually determine those impacts. And one of the things that we did here at Cadmus, working for the city of Portland, was to provide measurement and verification services for the city on about 25 different innovative cutting edge green buildings. And many of those green buildings included green roof and green wall components. One of the projects was a family housing project that combined photovoltaics and a green roof. And we went in and verified the system was working, did some measurements on it. A second one is a mixed-use condo tower, which on the ground floor has restaurants and also houses the architect who designed the building. And I can see it out my window, and I can watch the wind turbine spinning about 14 stories up. Another project was the Central County Library in Portland, which is one of the most used libraries in the country. That building installed a green roof as well, primarily for stormwater treatment. And then another project that we looked at was a home where the architect who has been very active in installing green roofs for customers, put one on his home and also put a green living wall on the side of the home. So some very interesting projects. I've been following kind of the assessment of green roofs for some time. Worked with Dr. David Saylor in developing a module for Energy Plus that actually analyzed evapotranspiration, thermal mass impacts, and conduction impacts of green roofs to determine how they affect the energy consumption of buildings. and been also really interested in these stormwater impacts and sort of how different factors such as the material itself, the thickness, the location, and the type of rainfall, and all that might impact the ability of the roof to handle stormwater. So these are some of the things that I think are very interesting aspects of green roofs, as well as things like growing crops, which I think some of our panelists can talk about today. So with that introduction, I'd like to go around and ask each of the panelists spend a few minutes talking a little bit about some of their experience that's relevant to this topic that we're gonna go over today. First, Bob, if you'd like to kind of tell everybody what you've been working on.
Sure. And again, thank you. It's a pleasure to be on the panel. In 2006, I began a multi-year study to look at the potential for biofilters such as living walls and green roofs to be used to convert wastewater into a water resource. And specifically, the questions I wanted to address was, could these systems be used to not only clean the water, but while cleaning the water, reduce the energy needs of a building and concurrently grow agricultural crops? So in doing that, at Penn State University, we have the benefit of the Center for Green Roof Research, where we have 6 replicate buildings. And these replicate buildings, half of them have green roofs, but they measure 6 foot by 8 foot by 8 foot tall. And each building has approximately 24 temperature probes, not only on the exterior and interior of the building, but also within the cavities. So the wall cavities, the ceiling cavities, as well as the floor cavity. And in the profile of the green roofs, from the roof base all the way up through the plant canopy, we can measure the various changes in temperature if, for instance, a living wall is added to one of the faces. And so with that, and within these buildings, each one has an air conditioning. One door, no windows. So it's very easy to be able to tweak something and see what the resulting impact is. What I was able to do then with that is to place a living wall on the south side of multiple buildings. And the reason for the south side is State College, we are at around 40 degrees north latitude, and consequently the sun during the middle of summer, June 21st, the highest peak of the sun is around 70 degrees above the horizon. So the optimum impact to a building is on the south side. And this, of course, is important when you look at various studies, where they're located at from a latitude standpoint, and then where they place, whether it's a living wall, the green roof, etc., on the building's orientation. So one of the things in looking at this is how could I clean the water and at the same time be gathering the reduction in energy. What I found from this was truly remarkable. Not only did we achieve NPDES permit standards, so we achieved EPA's cleanliness for water in less than 24 hours, but at the same time, the exterior temperatures of the buildings were reduced by up to 68%. That's important, especially from a urban heat island effect. But then what is the impact on the inside? We found decrease of temperature up to 28%. So again, major reduction. But what's most important then is how did it impact the energy use by the air conditioner? And we found that there was an 18% reduction in the energy use of the air conditioner from having a living wall on the south side. So not only did it reduce the temperature, it cleaned the water, and again, we grew agricultural crops. One of the other things that we observed that was quite fascinating is the time difference between when a maximum external temperature was observed and the corresponding maximum temperature inside. In a building without a living wall, the average time for that was 21 minutes. So very quickly, that heat is migrating through to the internal. And again, that's a result of how much insulation, et cetera, is in the building. But with a living wall on the external, that time difference went from 21 minutes to 244 minutes. Tremendous difference. And so that means that peak energy use is significantly decreased because that time period has been so substantially impacted. So the upshot of this research, and again, the details of this, a multi-year study, there's much data, and I've included then within this presentation slides and also references for papers that I've published on it. But water was cleaned. At the same time the water was being cleaned, the building envelope temperature and internal energy usage was significantly decreased, and we were able to raise a significant amount of produce. And one of the final thoughts with this is, in the United States, the energy used to operate central wastewater treatment plants is thought to be around 3% of our total energy use. By having functional architecture, such as a living wall, green roof, that can treat wastewater at the source and decrease the energy use, it's also offsetting the amount of energy that would be otherwise used to treat wastewater off-site. So there is definitely a major impact to the energy equation of a building.
Great, Bob. Thank you. I'm curious, are you aware of the federal building in Portland where they're installing like external vegetation that goes up to, I don't know, it's like 15 stories?
Yes, yes,
Okay.
and it's again, it's great throughout the United States. There's a number of applications now where it's being looked at not only for attenuating wastewater, but also for integration into HVAC systems. So there are a number of projects finally that they are integrating these types of systems.
Do you know if there's any monitoring that's occurring of that? Or?
I'm not aware of it. I'm not that familiar with it, to be honest.
Okay. Yeah, I drove by there yesterday, and the growth is up to about 50 feet now, so it's making its way up the building. So,
Incredible.
great, thank you. Karen, I'd like to turn to you now and ask you to talk a little bit about some of your experience in terms of estimating and measuring energy impacts of green roofs.
Sure, thank you. Yeah, I started to do green roof research in around 2000 when I was back with the National Research Council in Ottawa. And at the time, green roof was still really new, and people just asked me, well, do you know if they even work like in the cold north? And then we just say, well, you know, we just have to do it, and we just want to try it. And being an engineer, I just like to get my hands dirty and instrument a roof and to do that. So basically, it's quite simple. We take a test roof. It's about like 1,000 square feet in area, and we instrument half of it with the green roof, and the other half we just leave it empty. And then we bury a lot of sensor in it, just like Bob was saying, like with a lot of temperature sensor, heat flux sensor, and we also take up the water that we capture them and then put it through the flow meter. So that allow us to take a look at also the stormwater management ability as well. And the good thing is like the plant didn't grow so well, but then we did still get quite a good result from that. So from an energy standpoint, we were able to show that like in the cold weather, it doesn't really work so well in the winter. Like we are looking at sort of like about 10-15% kind of difference in terms of the energy saving that we would be expecting. But and then in the summer months, we still have very hot like summer in Ottawa, even though it may not be as hot as down south in the United States. And we can see about maybe like a 70-80% reduction in the heat transfer through that building just because of the green roofs. So we were quite happy about the result, and we started to work with other partners, with the city and also with other university, and looking at how do we actually put green roof on, let's say, Toronto and Vancouver. They have very different climatic conditions, and how that green roof is going to affect the performance. So that was quite interesting. And then we just kind of repeat the same thing, find buildings to do it, and looking at some of the manufacturers to donate sample and install them for us, and then we just bury sensor and then measure that. So that also allowed us to have some very interesting results, especially if we took a look at Vancouver, where it's much more mild climate, as Alan would probably know, being in the Pacific Northwest, and the performance is very different. And in this situation, we can use very thin green roof layer and to achieve also the same kind of performance that we would expect. So for example, we did one experiment at the British Columbia Institute of Technology. By working with them, we can demonstrate that even with a 3-inch growing medium, we can get the same amount of water retention, the same amount of energy saving as a 6-inch green roof. So that was quite impressive, because we are happy that even with a smaller amount of investment, we could get the same benefits for that energy impact and the stormwater impact for the building. So after doing that, we say that, well, we kind of understand how the climate and what we can do, but how about the product? Because there are so many products out there, like what worked and what doesn't. So what we did was similar to Bob. Instead of building 6 replicate buildings, we actually built little boxes. And these little boxes I'm talking about, they have about 2 meter by 2 meter in terms of roof area, probably about 1.5 meter tall. So they are like little cubes, but they were insulated, they were heat and cool just like a building, and they also have water capture as well. So again, we instrumented. So put thermocouples, heat flux transducer all over, in the roofing system, in the green roof system, in the soil as well, just to look at how the temperature flow across the roofing system, and to understand better which product works better and how do we configure them, and in order to get different results. So that was quite interesting, because we don't look at just the plant itself, but look at all the different components and how to put them together in order to understand what actually worked better. So that also helped me a lot now that with a green roof company, to be able to develop products that would be able to satisfy if an architect want energy benefits or stormwater benefits as well.
Karen, can I ask you on these small systems that you were talking about, kind of how you scaled up the results, or how you were able to kind of, determine how they might affect like a full scale?
Right. Yeah, for the small system, we basically are looking more at the product. So we are looking just directly for each module, how that impact would be. So basically, the scaling up is more or less just giving those results to the engineers that are working on that whole building simulation. And they will ask us to give them a certain value, and then that way, taking that the result, they will be able to put into their model. So, so because they are not really like a real building per se, but some of the data, especially with the stormwater, they were able to extrapolate into their own building in that situation.
Okay, great, thank you. Chris, I'd like you to kind of follow up and talk about some of the interesting things you've been doing.
Yeah, thanks, Alan. At Bureau Happold, we've been looking at some high-performance building concepts, and one of those is one that came out of Europe in late 80s, early 90s, actually grew during the 90s, and that was called the Passivhaus standard. It was developed in Germany. Heidelberg is sort of the capital of Passivhaus concepts. I don't really want to call it a technology. It's more of a building design concept. And the idea is to minimize the amount of energy that's required for a small building. It's typically residential. That's where it really came out of. Although it's certainly being applied to commercial buildings now. But it came out of Germany and Scandinavia. It's been very popular there. However, in the U.S., it hasn't caught on. Part of it is that it's not so much some of the technologies that are applied to the concept, such as super insulation and low U value windows and heat recovery, ventilation, things like that. Those are all technologies that are being applied to buildings now. However, it was they kind of went a step further and to get the numbers that they said were possible, where you could really start thinking about eliminating the heating and air conditioning, except for dealing with ventilation. It affected lifestyle a little bit. The way the standard is based is they actually say you can only use a certain amount of energy in a given year. There's also another one where you can cap the amount of power, but the idea is to minimize the amount of energy. Well, there's more that determines the amount of energy that you're going to use over the course of a year than just how much insulation you have. There's also how much energy you're generating, and which means heat and electricity that you're using and generating inside the building. Now, that goes both ways, and in fact, the passive house idea was that, as it was developed in cold climates, that what you do inside helps heat the space. So again, keeping along with the idea of it being a residential area, you come home, you turn on the stove, turn on the TV, turn on lights, and all this adds heat to the space, and it can do it rather rapidly. And if you have a really well insulated house, then it'll you should be able to get to a comfortable level fairly quickly, or with minimal heat applied. And again, this was all developed in northern, drier climate, but now as it's being looked at in warmer climates, and in the U.S. we have a much broader range of climates, and we try and simplify the rules as much as possible. You'll still see super insulation applied, but you run into, again, lifestyle issues, aesthetics. How are you really using these spaces, and do you really need to put literally a foot of insulation into the space? Do you need to spend a lot of money on the windows? In a cold climate, they pay for themselves, but in a milder climate, you don't really need to do that so much. You can go to places like living on the beach in Southern California, in Key West. We got a lot of spots in this country where you don't insulate homes, except maybe a token amount to deal with the in California, you may get some cold nights or something, but for the most part, it's just very mild. You usually have windows open, and which is kind of interesting because from a numbers standpoint, that doesn't work so well if you're trying to maintain certain temperatures and so forth. But we found that with natural ventilation, that you can stretch your thermostat a little bit. You can let it get a bit warmer in the summer and a little bit cooler in the winter. When you have fresh air, you've got natural light coming in, and so what's happening with passive houses is now that it's being looked at by a broader audience, and the green building industry has really grown so much in the last 20 years that it has matured along the way. And if you were to go to Wikipedia and look up about Passive House, some great information, but it's like, yeah, is this it? Could we be doing a little bit more? And you'll see some hints of sort of next steps in Passive House design, and green roofs are a big part of it. Saying, okay, we're in a milder climate, or we want to do a design where we want to look at the cooling aspects and how vegetation. If you've got 100% vegetation on a surface, you're essentially getting rid of all your excess sunlight. And so if that's all you're having to deal with for your house, then put up a green roof and you won't have to deal with it. I mean, it's really and now you've got a living house. So aesthetically, from a quality of life standpoint and from an energy standpoint, it all you get a bigger package than just the numbers of hitting. You have to be under this certain energy usage during the year. There's more to life than that. And that's something that's being recognized. And so I think for when I've done some of my blogging and research and so forth, and looking at locations where green roofs are really beneficial, they're most beneficial in milder climes. LA is a absolutely prime example of where you can really maximize the benefits, especially with low, 1 and 2 story office buildings, and certainly with homes. And now with living walls, you can start looking at the whole envelope. And that's just like Bob was describing it, you've got you start looking at not just how are you looking covering the roof, but when you're looking at the walls as well, and you start looking at the numbers, and then you stand back and you look at these buildings and you're going like, wow, this is pretty nice, and you're opening windows and enjoying the space so much more. So quality of life is starting to come into this idea of passive house, and not just hitting a number, and so it's definitely being seen as a next step, and definitely being seen as a way to take advantage of more of more natural and acceptable ways of stretching what are you requiring from the space. So it's a really it's a very promising, and for architects, definitely a very exciting way to go.
Great, thank you. I wonder, Chris, I actually, a friend of mine in Portland recently built like adjoining passive house, and he said one of the problems they had was actually finding the components that met the requirements in the U.S., in particular
Yeah.
the windows, which kind of surprised me. Is that really the situation? Is that improving or changing?
Yeah, well, the thing is, I mean, obviously the products are out there. The question is where can you get them, and it might be a little bit more than going to, I don't want to buzz market any home goods stores, hardware stores, but it's just going to the hardware store and saying, building supply or whatever, and saying, okay, what windows do you have? In fact, there are some really good double pane windows with really good coatings, and using especially wood frames, but also fiberglass frames. You can get some pretty low U values on some of those windows, and a lot of it is window size and location. And that's part of it too. Is some of the passive house examples that I've seen. The quite often the windows, there's very few windows. They're strategically located for energy, and that's why I'm saying I think being able to stretch a little bit, loosen up your thermostat a little bit, and quality of life improves. But for wanting to work with, and especially do like bigger windows, yeah, you do have to pay. I mean, you have to look a little harder and pay a little bit more to find the windows that work. But they're definitely out there. Yeah.
Thanks. Well, I'd like to circle back and kind of close our session talking some more about this concept of integrating sort of green building components in passive house and net zero buildings too. But in the meantime, I thought it'd be useful to kind of open it up to each of you to talk about some of the factors related to energy impacts of green roofs. And so for somebody who, isn't as experienced in this area, what kinds of things should they be considering if they want to, actually derive the best kind of energy impacts? What kind of medium should they look at? Are there certain locations that they should just not consider? What kind of building? So um, just take it away, whoever.
Well, I'll just throw out just initial building geometry is certainly very important. So if you look at three different major types of buildings, so we have with residential where you have almost a one-to-one wall to roof, and then take that to a skyscraper where you have a huge component or walls versus smaller roof area, and then to big box stores which are predominantly roof. And so what you do then, how you optimize the efficiency, really is dependent upon what type of geometry you have. In my home here, where I'm at right now, I have 3 green roofs, and one of those I've integrated with living walls, and I use that for most of my agriculture because I'm in a very heavily wooded area here. And so it works out very well, and in addition I get all the other benefits that are well touted for what living walls and green roofs can do. So, but building geometry and then your orientation, as I mentioned, for northern latitudes, that southern exposure is the one that you want to optimize during the colder time, and of course minimize during the brief summer months that we have.
Which is actually something that that I've in trying to put together some fundamental materials for basically just trying to get fundamentals of energy with green roofs. One of the things that you start doing is you start looking around for how does nature work with vegetation and from an energy standpoint. And one of the things that happens in the springtime, you gotta get the ground warm as quickly as possible, especially in northern climates. You got a short growing season, and so where you have a lot of deciduous trees, that's part of nature's strategy is to to lose that foliage in the wintertime and let some sunlight in. And then in the summertime, you fill up the foliage, the leaves are, the trees all fill up again, and you start blocking the sun, shading the ground to keep from just scorching it, unless you want to just dump a ton of water on it. But you look at some of those strategies that nature's, and it's not, I guess you could call it, it's not really biomimicry. You're using biology, right? And with a green roof, and so I love seeing people wanting to apply that to, especially to the side of a building, and I was thinking about this with some of the issues with Passivhaus, is basically having vegetation, and set up on a structure where you've got the sunlight coming in, and like basically over windows, right? And so that in the wintertime, the foliage goes away, the sunlight's coming through the windows. In the summertime, it starts giving you some shade, and you don't want to get too crazy with it. But it's something that I'd love to see designed into more buildings.
And talking about plants, and you mentioned, like Chris mentioned about the plants losing their foliage in the winter and allowing more sun to come in. It kind of makes sense that if you have the plants like around your house, and on top of the roof, sometimes what we observe quite interesting in Ottawa, especially we have tons of snow. Like sometimes we have about 8 or 9 inches of snow on top of the roof. And the snow itself is an excellent insulation. So you want to capture that nature, like take advantage of that snow. So I actually noticed, quite interesting, one day I was walking into the building, and then I noticed there were this low juniper plants. They're about like a foot tall, and they're just like horizontal. They're called horizontalis, meaning that they actually grow horizontally. So they're like a little umbrella, like hand holding all the snow on top, like with all this little like pine kind of look like foliage. So it's actually really cool, because if you put your hand through that snow underneath, and you actually get like a foot of airspace, and that also is a bit of insulation. So just like Chris mentioned, take advantage of the nature, not necessarily mimic it, but if you can put this kind of plant on top of your roof, you capture more snow, you get some insulation, and that's all the better as well.
And another analogy that goes with that, if you think of what happens to a pond or a small lake in the wintertime in the northern latitudes, they will freeze over. Again, all the amphibians, etc., will go down into the mud because those areas don't freeze. And so you have this top layer that's at 32 degrees, and especially with a winter like this, when you can get down to single digits, etc., well, those areas below now are protected. What I've observed with green roofs in the northern latitudes, they will freeze solid. And so you have, in essence, this block of ice. Now, a number of studies have looked and said, well, with moisture conducts heat. But I think once it's frozen solid, now it acts as an insulator across it. So during the wintertime, I think that there's actually a movement that you may lose heat for a while, but then with the freezing of it could actually cap it off.
And I think a lot of that's because of the voids you have. Like when soil freezes, unless it's saturated, it's not going to freeze solid. So you're freezing a lot of voids into it, and I think that's just like with snow. It's not too different with snow, right? That's I think that's a big part of that.
Yeah, and also I'm looking at from a product point of view. For example, drainage product. If you have a drainage product that has little cups, like a dimple board or whatever you call it. And then it captures the water and that frozen solid in there. So just like Bob said, it's conduct heat. But what if you just have coils that just allow the water to exit and you never have frozen ice in there? Then now you get an insulation layer, just an air layer, but you don't have the conduction, but you prevent any air movement, so it's like prevent the convection heat transfer as well. So just by little like improvement in your product, that you can actually try to improve your system performance as well. And when we did the experiment by putting thermocouples across the snow, when you have the 9 inches of snow on top, you don't see anything underneath that 9 inches. And we actually observed the outdoor temperature could be minus 30. And in Vancouver, in Vancouver it's hard, but in Ottawa, you can get minus 30, minus 40 quite easily. But the membrane temperature sometimes is only like minus 10, 0 degrees. And that's about it, under that much snow and the ice of the solid block. And what we observed quite interesting is with that solid block of ice, it also takes time in the spring for it to actually defrost. Sort of like your frozen turkey, you kind of put it in your fridge and it takes days before it defrosts. It's the same thing. It's a bit of a thermal mass effect too. So that moderates your heating and cooling and just kind of, I wouldn't say insulate, but like making it, the moderation, the fluctuation less severe.
Yeah, I think these are all really good design, guidance for people. And I would just comment that I mentioned some of the projects that we studied in the city of Portland, and one of them, they used like photosensitive glazing that changed, got dark in the summertime when the sun was shining in, and they put it behind some trees, which in the summertime had leaves on them. So that was not a really good engineering strategy, because the effect of the glazing was negligible. So I think you really, point from that is you really have to think through this stuff. I'd like to ask, while we're still talking about energy, what thoughts you have about what tools there are out there that would help people who want to actually predict the impacts of different, green roofs and walls on energy use.
Well, it's from, having developed the calculator and doing all the energy analysis that I've done on buildings, really what it comes down to is a green roof. 100% foliage coverage can be looked at as a perfect reflector. I mean, really, it gets rid of all the excess sunlight. And the other big aspect of it is the thermal mass. Unfortunately, I think some of the more common tools that are used for building energy analysis, some of the DO2 based programs, don't handle the thermal mass very well. They just, I have found some problems with the algorithms that they use. Otherwise, it's really, you kind of play with this 100% reflectance thing. Otherwise, it starts getting very involved. It's a really good first order approach. Otherwise, it gets tricky. It gets difficult to try and account for all of the convection, conduction. It gets pretty complicated once you get away from the simpler, exactly in the end, what is it this vegetation is doing.
And if you add water to the system the way that I do, so you'll have natural evapotranspiration going on within the systems. But when you then augment it with the water as I do, what I found is an evaporation rate of 1/2 gallon to 1 gallon per square foot per day. And so just to put that in perspective, it takes about 8,700 BTU to evaporate 1 gallon. So within a very small wall or a roof, you have a tremendous amount of energy being consumed in the summertime, and with the resulting cooling. And again, this can just dramatically impact some of these programs depending on how they look at evaporation. So the plant species that you're using, whether you're augmenting with water, and again your overall climatic conditions, humidity, etc. And so you get this long range of wide range of what actually the roof or wall can do.
And I think one of the things about the energy modeling is a lot of them are more related to building. But in terms of the living plant and the soil, there are not a lot of data out there. Just like I went to one of the presentation about different type of plants, and then I'm not in a plant background, but I'm very much amazed how different type of plants. Some of them, they have more like a gray foliage. Some of them, they have hair on the surface. And all of this can actually like improve their thermal performance. But this is not something that we normally would put in an energy model in terms of like for a building. And so those are very specialized module that would be interesting to incorporate.
And so when you're looking at the different kinds of plants, what's really fascinating is to look at plants in desert regions and how they deal with it, because where you don't have the water, right? And it's like, okay, well, I don't get my gallon of water a day, so how do I keep from cooking? And the temperatures of the foliage and a lot of those plants will, it'll get above the ambient, but not much. When you start looking at your differences in temperature that really count for how much heat is moving into a building, it's still in a very small range, if you will, and so yes, they use whether it's leaf area, leaf angle, how they fold, how they're veined, how the little hairs on a lot of these leaves, and then you look at succulents and how how succulents use their internal mass and liquid to be able to take advantage of cool nights to stay warm during the day. Yeah, that's what I mean. That's as I started looking at these, trying to validate the calculator that I created. It started to get a little bit overwhelming, and I thought, boy, how do I get this across, and how do I be confident that this is really applying to all these plants? And what it came down to was they all have their own way of staying within a certain number of degrees of ambient temperature, and it's fascinating. I'd love to see more research just on the thermal. Just looking at how the thermal aspects of plants, and not just from a biological standpoint, but from a mechanical engineering standpoint. It sounds funny, but there's a lot of mechanical engineering going on in nature, and yeah.
Several years ago, one of our doctoral students looked at various types of sedums as well as different medias, and then looked at the reflectivity of these media and leaf structures, their ability to absorb, presented a paper on it several years ago. And again, there's so much variability within all this. The models are getting better and better, but again, there's a tremendous amount of variation yet.
Okay, so I wanted to move a little bit to talking about stormwater and water treatment. We touched on that a little bit earlier, but some of the same, I guess, issues that apply there. What kinds of things should people take into account if they want to use their roof to capture stormwater, reduce stormwater runoff, or treat the water that falls on the space?
But I'll add one caveat that we often find. Too often designers think, well, if 4 inches of media is great, then 12 inches must be fantastic. And so again, they have to remember hydraulic gradients, etc. And so there's decreasing returns as you increase the amount. So we really find with extensive roofs about the optimal is around 4-inch media. But that's an important part when you design and you're looking at stormwater as being one of the main driving points.
Yeah, absolutely. And I totally agree with what Bob is saying. When we did an experiment, actually with a 3-inch growing medium with sedums, and then another which is a 6-inch growing medium with grasses. And one would expect you double the amount of growing medium, you should double the energy saving or the stormwater retention. But what we observe is in Vancouver, at least we're in a rainforest type of climate. We have about 1.5 meter of rainfall per year. And the funny thing is, everybody thinks Vancouver is wet, but we are only wet during the winter. and we are really, really dry in the summer. So about like 70–80% of the rainfall just fall and from October all the way to, let's say, March, April. And then from that on, it's dry, dry, dry. So now with that much rainwater, and sometimes it can be like 30 days, every day you will have rain. Even if you have 12 inches of soil, everything is soaked, and then you cannot capture anymore, just like a sponge is fully saturated. And that's what we observe in the winter. The stormwater retention is maybe about 15%, and it's like hardly any. But you're talking about 15% of, let's say, 40-inch or like a meter of rainfall. But on the other hand, in the summer, yeah, you know, you have extra thickness is better, but then you're talking about like 30–40 millimeter of rainfall. So it's not like an inch, a couple inches, not a lot. So then overall, you're looking at the difference is hardly anything. And also another funny thing that we observe in the winter months is actually the 3-inch green roof does a little bit better than the 6-inch green roof. And at the beginning, I thought, you know, something was wrong with my instrumentation and all that. But then I realized later on that, well, when you have, in the winter, it's not very hot, and also it's very high humidity outside because it's always raining. So that it doesn't have much chance for the water to actually evaporate. So once you get soaked in, and that's it, and it's just like a thick, wet blanket, and it's not going anywhere. So you don't get to evaporate it, you don't create that capacity. You have to dry a little bit and then create a capacity to be wet again. And you don't get that. So it's not a big difference, but we do observe it consistently. The 3-inch actually work better than the 6 inches. And in a way, like we're saying that, just like Bob said, well, you won't want the diminishing return. You want somewhere that it will be good. And for us, Vancouver seems like 3-inch work well, and even less than the 3-inch we observe is quite well as well. But obviously, if you're in other weather, you might want like 4-inch or 6 inches, depending. And that would create some calculation and energy and stormwater and so on to actually calculate what is still ideal. But just for just a general rule, like there's no one-size-fits-all solution, and it's not always more growing medium is better. And that's very important.
Yeah, especially I'm glad you're talking about, you know, like with climate and humidity and so forth, because it's such a huge issue with not just with how you deal with stormwater, but how you deal with from an energy standpoint as well. Especially you were talking about the swamp coolers popped into my head, and they've been a very popular way of cooling houses and buildings in desert areas where it's very dry, but they're also using up all their groundwater. So, but these are all factors you have to keep in mind. Is you're right? It's not one size fits all. A 3-inch medium is going to behave very differently in Arizona, higher elevations of Arizona than it is going to be in, lowlands of Minneapolis. I mean, it's a, big difference between, low humid areas, high dry areas, and yeah.
Yeah, I think same thing with energy as well,
Oh, absolutely.
Yeah. It's just sort of like it's the same like a battery, like a thermal mass. You absorb that, you release it at night, and so on. And you have to have that sort of cycling in there, and the diurnal changes. And how much do you need to capture? It doesn't have to be that much sometimes, like for most climate.
Yes, but as you go south, then you definitely, they have a trade-off. They need that thermal mass, so that they definitely have to go with a greater depth, but it's not for stormwater capture. In that case, they need that thermal mass with it. One of the other things, just to circle back, you think of so many commercial buildings, they put their HVAC systems on top of the roof. And when you look at the temperatures that we see, 40 to 50 degrees, even up to 60 degrees centigrade on a roof, and they're bringing that air, that's their air intake.
Yeah.
And yet we know that green roofs will give you typically, it's putting in down less than 30 degrees as a typical summertime temperature. So the ability to control that air that's coming in. We haven't conducted any studies around air intakes, but I'm looking at designing a study for that this year, where we can compare and see how much would, by putting a green roof around air intakes, would it decrease the actual energy use, and not just the energy use, but also you think about with HVACs coming on and off, having to cycle. If we can decrease the amount of cycling with them, that would also be beneficial.
Well, that's interesting you bring that up because we are actually working with a big box retailer whose name I probably shouldn't mention, but we're doing exactly that right now in
Excellent.
Portland. So we hope to have some results in a matter of months.
Excellent.
Yeah, and I think the greatest impact is where you have intakes on a roof.
Yeah.
You have the cooling fans for the DX units, whatever compressors, but it'll affect the efficiency a little bit. But the biggest thing is in especially in the summertime, doing whatever you need to do to try and help cool down the air that's coming in through the intakes.
Yeah, and that's what we're trying to measure, that effect.
Yeah.
So interesting.
We did do a little bit of measurement by actually measuring how far on top of the roof that the green roof start to see the effect. Because obviously, if you look at the roofing membrane, if you can easily get, like, I'm sorry, but I have to use a degree Celsius, but it's almost like 70 degrees.
Oh, come on.
Like on the roof, but on the green roof, obviously, it's only about like 30 degrees or so. But what we observe is if you go above, like the air temperature above that, usually up to about 8 inches, you start to lose the difference between the two. Like you will see a big difference right at the surface, but it's not so much. I think it's the air convection and so on that actually like equilibrize the temperature. So I think where you take your air intake could be quite important too.
Right. That's exactly right. And so that 8 inches, that's the boundary layer that you would have on the roof, which is something I actually take into effect in my calculator. Yeah. And yeah. So if your intake is over on what you'd say the leading edge of the building, then yeah, you're going to get fresher air coming in. But you also don't have if you are able to get any extra cooling from evapotranspiration or just because you've been able to keep some cooler cooler stuff down below from the night before, having it blow across that before it gets to your intake that'd be a great strategy. Yeah.
But so those are the exact results that we've seen that Karen's mentioning, is that you don't see the impact very far above. So part of what I was thinking, Alan, I don't know if y'all are looking at this, is integrating living walls then around those intakes. So you have on top of the green roof, then you have the small living walls, and you have to let them out far enough so you can have an exchange of air. But if you can use those that you're pulling the air through, now again you can get that evaporation that would optimize it.
Great, good idea. I'd like to just talk really briefly about one other benefit that some of you have mentioned, that's growing crops. Bob, in particular, you brought that up. It's a fascinating idea, and I'm curious what the status is of that, and kind of what kind of crops make sense, and how you harvest them, and things like that.
Well, on my roof, I have everything from kiwi to grapes. One of my goals is eventually to bottle a bottle of wine from my roof. But the majority of my crops are greens, microgreens, various types of lettuce, spinach. Have strawberries, different types of herbs. I do a lot of cooking, so I enjoy being able to just walk up to my roof and pull out things that I can use in my kitchen. Tomatoes do extremely well. I focus primarily on the smaller variety tomatoes, but then I've done range of eggplant, squash, peppers. Peppers do extremely well too. But all that said, there's a couple of things you have to be careful with. One are regulatory issues so far as utilizing any type of wastewater. In some states, such as where I'm at, Pennsylvania, Maryland's another example, they are very restrictive when it comes to wastewater reuse. And in fact, Pennsylvania does not really recognize gray water. And so this is a big issue. There's concerns about pathogens, although my research so far shows that when you put them into these integrated biofilters, it's as if the microbial communities that are already associated with them treat some of these organisms like fecal coliform like candy. They disappear very, very quickly in the systems. But there are regulatory concerns. Now, the other one is within media. You have to be careful. In the past, some groups have looked at utilizing ashes and things as a component, and those can have heavy metals, especially arsenic. And so you have to be concerned because some plants, especially the cruciforms like cauliflower, broccoli, etc., have the ability to uptake metals preferentially. So there are certain things you want to look at, but I integrate these systems together. So I put living walls with the green roofs, and I find that works out great for optimizing vegetables.
So in New York, I've been paying a lot of attention to urban farming, and we've been growing some pretty serious gardens on our balcony. And so yeah, it's a little different concept, but one of the things that we're seeing, especially with more expansive, more almost industrial scale urban farming, is one of the things that gets eliminated is the cost of transporting, especially with lettuces and microgreens and things like this that grow so well in per square foot, that not having them trucked in from 100 miles away, they're potentially can be priced at a low, lower than what you would normally see in a grocery store. Still getting there because a lot of it's grown hydroponically, and what I'd love to see is, we've got some rooftop farms. I think they could be laid out a little better. We're all still figuring a lot of this out. Of course, I've got my ideas of how it should be done, right? But it's definitely there. So it's all aspects. It's not just what you're doing with the building. It's also getting food to people that's fresher and at a lower price. Ultimately, that's the goal.
And I find that it's getting more popular in Canada as well with the rooftop farming. And I also work in Asia, and I find in Asia, actually, rooftop farming is quite popular, perhaps because people are more used to farming to start with. And secondly, in Asia, usually the cities are so crowded. And if you do have a rooftop, you're like gold, and you want to use it. You don't want to waste it. It's not like here. We just live it like, I don't know, like for them, they would put tennis court on there. They would put rooftop farming. And actually, a lot of schools are starting to put rooftop farming because they want to teach the kids where their food come from. Because a lot of us just don't know where things come from, and they get to involve the kids and as education program. And I think that's really, really great idea too.
Yeah, it was actually a trip to Guiyang, China, that I was there for a week. And yeah, I was, from my hotel room, I'm overlooking these apartment buildings. They were just amazing, and they're all vegetable gardens. I mean, everybody's like going to grow their own food. The number of half the balconies would have strings run up off the railings for beans, right? It was just amazing how much food was being grown on rooftops and balconies there. Yeah.
I had the opportunity a couple of years ago to teach at a university in China, teach in the Department of Environmental Engineering regarding sustainable technologies like living walls, etc. And I took the opportunity to visit a textile plant outside of Shanghai on the way to Hangzhou. And Karen, you probably know this one, but this gentleman was very concerned about the quality of the food that he was providing to his employees through his cafeteria. So he, in essence, took the top of his buildings, nearly 3 acres, and made extensive vegetable gardens. It is incredible. I've visited a lot of rooftop gardens. I've never seen one to this extent. The interesting thing, though, is he imported soil from Norway. He was concerned about using Chinese soil.
Wow.
And so he defied some science there. Because, of course, from atmospheric deposition and stormwater, etc., you would still get that contamination eventually. But his growth and his production is just amazing. And he has a chef on site that produces everything for the cafeteria from the food that they harvest from up there. So he's definitely demonstrating that it can be done.
Yeah, I thought I'd mention that one of the projects that we studied for the city of Portland was a restaurant, and at the top of their four-story building that they were in, where they were located in the top floor, then they had a green roof on top of that, and they were growing all their herbs and everything
Yeah.
up there, and that was just fine. But they were also raising chickens on top, and that ran into a problem with the city inspectors, and I think the concern was that chickens might get loose and fly off, so they put an end
Eh,
to that.
I think part of the problem is that they don't fly very well. So
That's correct. Yes.
that
Yeah,
yeah,
fall off probably is a
yeah.
better description. So we're just about out of time here. I guess I want to wrap it up a little bit, but I'd like to get some feedback from everyone because we've talked a lot about kind of all the different aspects of the vegetative components in buildings and the interaction with the building as a system. And I'd like to hear kind of what your thoughts are on where these can be providing benefits in sort of the passive house concept or the net zero energy building concept, because California code building code is going to require all residential buildings to be net zero by 2020 and all commercial by 2030. So it really means taking a look at the building as a whole system. And I'm wondering what ideas you have about how you might incorporate any kind of green building, living building components into that framework.
I talked about it, but Bob or Karen, if you want to throw in your 2 cents worth on that.
Well, I'll just throw in one thought with it. Back in the 70s in industry, we started to integrate constructed wetlands as an alternative for treating wastewater. And they worked great, but the problem was they took up so much space. And so that was one thing, looking at how we can start making functional architecture. And so by integrating biofilters, taking green roofs, living walls, and actually miniature constructed wetlands, when you integrate these systems together, now you have a functional architecture that can fit into very small spaces and actually are very, very much more efficient at whether it's treating pollutants or doing some of the other items that we want to derive from them. So I think that we're pushing the technology so that it can be better used. And one of the things, though, that I find so often is when we start looking at utilizing these systems for wastewater, et cetera, there is some regulatory pushback at this point because it's felt that these are very different systems.
Yeah, I think any new technology seems to be always some pushback from the government. But I think we should just like continue to do it because there are so many rooftop, and just like Chris said, like when he looked out from his hotel, like all these Chinese people are using the rooftop, and it's just so much of a waste we have here. And I just really hope if you want to do something, just go out and do it. And then just like PV, like before, like and also like having the energy back to the grid. Before it was so difficult, but now, like after so many years, it's become like law and become so much easier. And I think if we just continue to do it, eventually the government will be pushed back, and then it will be fine, and we'll learn from it. So we should just go ahead and do it.
Yeah, I think especially with these regulations that boy, architects and developers are going to be looking for the solutions that they can think about the least. In other words, just like putting some imagination into something is a huge investment for a lot of these people, and so basically the simple answer is like, well, throw PVs up there. And yeah, I mean it's from a pure energy standpoint. There's a lot of competition there with green roofs, right? It's a tough trade-off, and so I think that's going to be that's the real challenge. Is can you see the same benefit from having a green roof as you would some PV panels, while also having the benefits of what's happening with wastewater and so forth. And you have to start looking at, from an energy usage standpoint, looking at everything that you do with what you have when you're dealing with this property. And we're going to have to, I think, looking at it from a single building standpoint is short-sighted. That we need to be looking at it more from a neighborhood standpoint, and taking advantage of the diversity of schedules and usages that you see in whether it's an industrial area or residential. But you know, this is all coming about very, very quickly. You know, we're making this up as we go along, and we'll get there.
Yeah, yeah. Well, I think the growth of PVs and installation is a good example of how something can happen really quickly once it takes off. So, I think with that we'll wrap it up. I appreciate it. I think really thank everybody for their help and really thoughtful comments. And I hope this is a very useful panel for everybody who views it.